Welcome to Luxoft Tech Talks, a series of podcasts in which IT gurus share their knowledge and discuss the latest trends and innovations in the world of IT. We are going to cover the most recent developments in the programming languages, frameworks, and technologies that are shaping the future of the software industry. This new format of online learning is part of Luxoft Learning Management and Development Services rebranding. Please share your feedback in the comments to let us know what speakers and topics you would like us to cover in later installments.
Hello, everyone, and welcome to the first in a series of Luxoft Tech Talks. I'm Rex Black, president of RBCS. We are a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. We've been around since 1994, delivering insight and confidence to hundreds of clients around the world, with our team of international consultants that deliver customized training, consulting, and expert services to companies looking to improve their test and quality assurance practices. I've been involved in software engineering since 1983, primarily testing, test automation, and test management, and I've written 14 books on the topic of software testing. So the first in this series, we're going to talk about code coverage metrics and how you can use them to improve the thoroughness of your testing. So code coverage metrics are a way to measure the extent of your white box test coverage. So by white box, we mean testing that's based on the structure, the way the system is built, how it is implemented. And we're going to look at three basic types, actually sort of four types here of white box coverage. So I've said three because the first set, statement decision and modified condition decision coverage, are classic control flow based coverage measurements. We're going to break those down into statement and decision on the one hand and modified condition decision coverage on the other hand, because they are somewhat different. We're also going to look at McCabe cyclomatic complexity and basis paths and the basis tests that are associated with those, and compare and contrast that with statement and decision coverage, and also explain the use of the concept of cyclomatic complexity from a testing point of view. And then we're going to talk about set use pair or data flow coverage and some of the interesting aspects of that, but also some of the frustrating aspects of it. And throughout this, we'll talk about tools and how tools can help make this process less tedious, because going through and counting coverage by hand is typically not something that you want to do. There are times when you need to do it. Currently, I'm working as an expert witness on a case that it does involve manually auditing a number of unit tests to check their coverage. And it is something that can be done. And of course, when I explain these concepts, you'll see how it could be done. But for the most part, you're going to be dealing with large volumes of code, and you really wouldn't want to have to do this by hand. So we'll talk a little bit about tools, how the tools can help. And we're also going to talk a bit about the limitations, what kind of bugs white box testing can miss, because one of the things that's happening lately that can be a little bit, it's a both positive and negative trend. The positive trend towards large volumes of automated unit tests put into build pipelines and used as part of an automated build and delivery system. Now that's all great, but the risk is that people sometimes over rely on it, and that can lead to missing important bugs. So we're going to talk about that at the end, about how to sort of contain your enthusiasm about these things, as it were, and make sure that you understand their limitations. Okay, so when we're talking about white box testing, first of all, let's be clear, we're talking about a dynamic type of test. So what is a dynamic test? A dynamic test is one where the code has been compiled, the code is being executed. We are actually submitting inputs of various kinds, creating test conditions through various mechanisms, such as data is loaded into databases, inputs being submitted, and so forth. And we are comparing actual results to expected results, looking for discrepancies between those, so-called anomalies, that might indicate the presence of defects. So that's to be distinguished from a static test, where a static test would be one that does not involve executing the thing being tested. We would consider a static test to be something, for example, like using a static code analysis tool, like say SonarQube or Fortify, to evaluate the quality of the code prior to running white box tests against it. Now, one of the things that's very helpful from a point of view of what, why white box testing is valuable and why measuring code coverage during white box testing is important is that if you derive your tests entirely from the requirements, say your user stories and their acceptance criteria, you can end up missing 80% or more of the code. Now, that might seem strange to you. There's actually some very solid both theoretical and practical explanations of why that happens, which I'm not going to go into here, but a considerable amount of the code will not be executed if all you've done is verify the user stories and their acceptance criteria, or the non-functional requirements, or business requirements, whatever kind of documentation you tend to get that expresses what the software is supposed to do, how it's supposed to behave. You may end up missing quite a bit of it if that's all you use as the basis of your tests. And so code coverage analysis allows you to look at what you're not testing. And complementary to that, you can then use white box testing techniques to figure out how to fill those gaps. So this is test design that is based on how the system works rather than how it's supposed to behave. And as I said at the outset, we're going to look at a couple general categories of control flow based coverage, and we're also going to look at data flow coverage and how data flow coverage could potentially work. Now, for the control flow coverage techniques that we're going to look at, including the cyclomatic complexity and basis paths testing, there are tools that will allow you to monitor how completely your white box tests have exercised the code. Now, hold that thought though. When we talk about data flow coverage, I'll note that there's something a little bit different going on there. So let's get into some details. When we talk about code-based testing or control flow focused code-based testing, there is statement coverage. Now, statement coverage, 100% statement coverage means that every executable statement that exists in the code has been executed at least once. And pretty much any programming language that you are likely to encounter in the real world is going to have this concept of an executable statement. There's generally a definition of what constitutes an executable statement in the definition of the language. Quite often, if you're talking about something like Java or C++ or so forth, it's a single line delineated with a semicolon at the end that contains various tokens that are understood by the compiler that get actually translated into machine code that gets executed by the CPU when the program runs. That's generally what an executable statement will be. And what we can say is, well, if we have a defect in the code, basically that defect lives in some executable statement, right? The bug is in an executable statement. Now, it's a little more complicated than that because the bugs can exist because of combinations of executable statements, any one of which is correct by itself, but together they cause a failure to occur. So when one statement creates a precondition that is unacceptable for a statement that's then executed subsequently, that could be the cause of the failure. But we can say then that the bug basically exists in those two executable statements. So if we have bugs in our code and we don't execute the statements that those bugs are in, we most certainly will not see the failures associated with those bugs. So statement coverage says, well, bugs live in statements, and so I'm going to focus on trying to execute every one of those statements at least once so that I've got a fighting chance of seeing failures associated with those bugs. Now, you have to be a little careful because just because you have executed a statement that has a bug in it doesn't mean that it has caused a failure. You can get things like what's called coincidental correctness, like let's say that the statement that I'm executing is supposed to be adding two numbers, but instead it's multiplying them. Well, if I execute that line of code with the input values of 2 and 2, I get 4 either way. 2 times 2 is 4, 2 plus 2 is 4. So I wouldn't actually see a failure even though the code is wrong. But certainly the other way around is true. If there's a bug in a line of code and I don't execute it, I most certainly will not see any failures associated with it. So that's the idea behind statement coverage. Now, decision coverage says, okay, in addition to having this concept of statements in code, we also tend to have decisions. I mean, one of the things that makes a computer programming interesting is that it makes decisions. It says things like, okay, if this is true, do this thing. Otherwise, if that is true, do this other thing. If this is true, do this. If it's false, do that. Or something along the lines of, while this pointer is still pointing at something that's not null, execute the body of this loop. And then whenever the pointer finally reaches the end of a list or the end of a queue or whatever it's pointing at, then stop executing the body of the loop. So those are called decisions. And in decision coverage, what we say is we want to evaluate each decision such that the decision was at least once true and at least once false. So if we have an if statement, we have done the true branch and we've done the false branch in the if statement. And that's because in some cases, there are bugs that don't live in statements themselves. They live in paths or branches in the code. So let's say, for example, we have a if statement, and in the true block of the if statement, we initialize some data structure. But if we do the false side in the else, either there is no else block or the else block does not initialize that data structure. And then subsequently in that same method or function or procedure, we execute a line of code that assumes that the data structure has been initialized. Well, if we have done the true side, the true decision, then the data structure will have been initialized. But if we have done the false decision, the data structure will not have been initialized. And so that statement will result in a failure if we have done the false decision. So this is the idea behind decision coverage. Now, there's another kind of coverage which is not typically measured, but is a constituent of a type of coverage that is called condition coverage. So condition coverage is, if you think about how the decisions are made, they are made based on Boolean expressions. And a Boolean expression contains one or more atomic conditions. So an atomic condition is one that cannot be further subdivided into pieces that result in a true or false value. So if we have conditions that are making the decision, which we will, then each of those conditions can be evaluated, and we can say, well, we want each of those conditions to be once true and once false. Now you might think, Jay, that sounds pretty much the same as decision coverage, but in a few minutes I'm going to show you an example of how they are actually different. Now, if we have compound conditions, like if A greater than 0 and B less than 0, then each of those conditions can be true or false. So multi-condition coverage is we want to make sure that we've covered every possible combination of constituent conditions. So in the example I just gave, that would be true, 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 false, false, true, false, false. So there'd be 4. Now, as you can see, multi-condition coverage, the number of tests that would be necessary to achieve it would double every time you added a condition, and that gets to be kind of painful. So there is a form of code-based coverage called modified condition decision coverage, which doesn't try to get to multi-condition coverage, but it achieves the same level of code safety. And what it does is it says that you have to achieve condition coverage. So every condition has to be at least once true and once false, plus decision coverage. So you have to have done the true and the false side of the decision, plus coverage of every possible combination of constituent conditions that can affect the decision. Now that's a mouthful, but don't worry, I'm going to explain that. One thing I want to point out here before we move on from the slide and I start showing you some examples is tools are available to measure statement coverage, decision coverage, and modified condition decision coverage. And those are the ones that are in actual practical use. The others are more theoretical and primarily of interest just to kind of illustrate the value of modified condition decision coverage, or MCDC. Okay, so let's look at some examples to illustrate this. So here we have a simple program, and what it's doing is it is producing a Fibonacci series for us. So we have to give a argument to it. So that's what's happening. It gives us a prompt that says, tell me how many elements you want. And then we give it an argument. We give it some integer number. And assuming that we gave it a positive number, it will then go through and create for us the Fibonacci series, which is what's happening in that loop. Notice it does allow us to do an empty series where if we give 0, it prints a open brace and then no elements and then a closing brace. So that would be a Fibonacci series with 0 elements. If we give 1, then it will print out 1 and so forth. So it has that ability to print out as long a series as we want. Now, of course, at some point, given a large enough number, it will overflow, right? It will exceed the capacity of the integer variables that are being used here. But that'd be a pretty large number if you're talking about 32 or 64-bit integers. Okay, so if we want to get 100% statement coverage, so you remember statement coverage, as I said, every executable statement is executed at least once. Now, by my count, there are 16 executable statements in this program. I wasn't really too precise about that, so there could be some wobblers there, but let's just assume it's 16. So if I test with, say, -7, so n less than 0, that's going to get me 37.5% coverage. It will not give me all 16 because, of course, it can't, because it only does the part of the if statement associated with lines 6, 7, and 8. It doesn't do the part of the if statement associated with lines 9 through 20. Now, if I want to get to 100% coverage, I would then run a second test with, say, n equals 20. And then in that case, instead of doing the true side of that n less than 0 if statement in line 6, it does the false side. It starts at line 9 and goes through line 20. And it also goes into the loop, as it will iterate the body of the loop 20 times, in fact, and produce a Fibonacci series that has 20 elements in it. Now, that's 100% decision, or excuse me, statement coverage. And you might say, well, some of the statements get run more than once. Well, yeah, they do, but at least once is the standard. Once a statement has been executed, it's considered covered and doesn't have to be recovered. Now, how about decision coverage? Well, if we run it, well, first let's look at where we have decisions. We have decisions on line 6 and we have decision on line 13, right? The decision on line 6 is do the true branch or do the false branch. And the decision on line 13 is do the loop or don't do the loop. So if we test with -7, that first test, that will have covered the true decision at line 6, but not the false decision. So that's an uncovered decision. And then for the decisions at line 13, neither the true nor the false has been executed. So you can see there's 4 decision outcomes, of which only 1 has been executed. So you have 25% decision coverage. Now, when I run with 20, n less than 20 less than 0 is false, right? So I'm going to take the false decision, previously uncovered false decision at line 6, and then I'm going to go down to line 13, and I'm going to go true, 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 a loop 20 times, and then ultimately the loop counter will get to the point where it's no longer less than 20. It will get to 20, and so at that point the loop will exit. So we'll have done the false decision. So I've done the true decision in the first test on line 6, and then on the second test I did the false decision at line 6, and the true decision at line 13 20 times, and the false decision at line 13 once. And so I've reached 100% decision coverage. Now you might say, well, okay, I get that, but isn't there really a second branch associated with that if that for statement at line 13, one of not doing the loop at all? And there is. So if you wanted to get to 100% branch coverage, you would have to add a test where you tested with n equals 0. So that test, you would do the false side of the decision on line 6, but then when you got to line 13, you would never iterate the loop. So this is something to be aware of, is that decision coverage, when applied to if statements, results in what you would expect, doing both the true branch and the false branch. When you get to loops, though, decision coverage, as long as you've done the body of the loop at least once and then executed, you get complete decision coverage for that loop with one test. And it doesn't force you to run the don't do the body of the loop test, which is not really what you would want. When we get to a topic a little bit later, I'm going to explain how you could set the bar a little higher and make sure that that actually does get done. Before we get there, I want to close on this idea of sort of like the classic code-based control flow coverage metrics. And this is multi-condition and modified condition decision coverage, which I mentioned before. So multi-condition coverage is, I'm going to test every possible combination of conditions. And generally speaking, if you've got n atomic conditions, that's going to require 2 to the n tests. So you look at the code, and this code on the right side of the screen is kind of nonsense, and it's just here to illustrate the concept. But if we have a greater than 0 and b greater than a, so multi-condition there, again, as I said, would require true, 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 false, false, true, false, false. Okay. Now, as I said, what can tend to happen is that, well, what will happen with multi-condition coverage is every time we add an atomic condition, so in line 1 there in the code, you have 2 atomic conditions, a greater than 0 and b greater than a. And those are joined together by a Boolean operator, which is the and. They're atomic conditions because they can't be split further and result in Boolean outcomes, right? So assume that a and b are both integers. So we're doing integer comparisons, right? Because we have relational operators there that are joining those two things together. So if we split a greater than 0 into a and 0, neither of those are Booleans, right? So that's the meaning of the word atomic. It can't be further divided. So we have a compound Boolean expression in line 1, and that consists of 2 atomic conditions joined together by a relational or a Boolean operator, excuse me. And so if we added another atomic condition to line 1, so a greater than 0, b greater than a, and c greater than b, then we would go from needing 4 tests to needing 8 tests. And then if we added another condition, we'd need 16 tests, and another would be 32. And obviously that gets out of hand. So if we want to make sure that we have tested the way the logic is working, and we've done it in such a way that we will reveal problems that are associated with the logic itself, which can exist. You can have situations where a bug is actually in a single atomic condition, and if that atomic condition gets evaluated the wrong way, it will result in a failure. So if we want to try to find those kinds of things, what people have come up with as a replacement for multi-condition coverage is what's called MCDC, Modified Condition Decision Coverage. So that's 100% decision coverage, meaning every decision taken, at least one's true and one's false. It's 100% condition coverage, meaning every atomic condition has to have been evaluated once true and once false. And at least one test where each atomic condition controls the overall decision outcome. So that if there is an atomic condition that has a bug in it and it results in the opposite outcome that one would expect, then it would result in the opposite decision that one would expect being taken, which would result in a failure. So now the nice thing about MCDC is that it gives you that level of confidence that you would get for multi-condition coverage, but you only need n+1 tests. So if you have n atomic conditions, you need n+1 tests. So for line 1 there, we would only need 3 tests rather than 4, which may not seem like a big deal, but think if we had 3 atomic conditions in line 1, for multi-condition coverage, we would need 2 to the 3rd or 8 tests. But for MCDC, we only need 4 tests, which is half the number, right? And it gets more dramatic as the number of atomic conditions goes up. So if we had 4 atomic conditions, you'd only need 5 tests rather than 16. So MCDC coverage is used in aerospace and other safety critical systems, vehicle systems. For example, there's a good 3 or 4 standards that require MCDC coverage. FAA standards, for example, and as the automotive standards, and as ISO standard 24262 or something like that. So if you're ever involved in doing safety critical systems, which, the Internet of Things and self-driving cars and so forth is getting more and more common, you will probably find yourself needing to be able to do MCDC coverage. Now, something to be aware of is that MCDC coverage, along with MC coverage, multi-condition coverage, so you don't have to worry about that because you won't be required to do that. But MCDC coverage, if you are required to do it, they can be affected by condition coupling and by compiler short circuiting. So let me just spend a brief moment describing those two things if you're not familiar with them. So condition coupling is a situation where the value of one condition is coupled or affects the value of another. So an example is in line 7. So see, what we're doing in line 7 is we're checking to see if the variable f, which is a pointer, is null. And only if it's not null does it make sense for us to ask what is being asked in the second atomic condition is the object pointed to by f, is it equal to 0? Now, so those two atomic conditions are coupled, right? So if the first atomic condition evaluates to true, then the second atomic condition can be evaluated to either true or false. Now, what can happen in this particular example, this is not true of all condition coupling, it's just true of this particular example. In this particular example, if the first atomic condition is false, so in other words, F is null, and then we go and try to evaluate the second atomic condition, what's the thing being pointed to by F? Well, we're going to get some kind of exception. You can't dereference a null pointer, which is what would be happening in line 7 if we tried to evaluate the second atomic condition if the first one had evaluated to false. So that's where short circuiting comes in. So in short circuiting, what happens is that the compiler generates an optimized version of the code such that the evaluation of the Boolean expression stops as soon as the decision is known. So short circuiting with regard to line 7 would say that if the first atomic condition evaluates to false, because the two atomic conditions are joined with an AND operator, it doesn't matter what the second or any subsequent atomic condition would evaluate to, the overall decision is going to be false, because false and true, false and false both evaluate to false, okay? And short circuiting works the opposite way around with an OR, where if we If the first atomic condition evaluates to true, then we don't have to evaluate the subsequent atomic conditions, because true or false, true or true, those both evaluate to true. Okay, so let me just show you how to design tests that will achieve MCDC coverage, because it's not entirely obvious, but there is a really cool little trick, a systematic process that will work for this. So what you do is you draw a table. It has 3 columns, and it always has 3 columns. Doesn't matter how many atomic conditions you're dealing with or how complex the logical expression is. So you write the logical expression in the first column, and then you write the true outcome over the second column and the false outcome over the third column. Because you see, ultimately what we're doing, again, remember, is trying to make sure that every decision has been taken true and false. So those are the 2 outcomes there. That's represented by columns 2 and 3. And that each condition has been at least once true and once false, and that every atomic condition has been able to influence the outcome of the decision. So this trick will work for that. So we have the 3 columns, excuse me, with the 2 outcomes in columns 2 or 3, and the logical expression in column 1. And then what we do is we add a blank row for each atomic condition. So you can see we have a row for A and a row for B. If we had 3 atomic conditions, we'd have another row. If we had 4 atomic conditions, we'd have another row. So what happens is, as the number of atomic conditions grows, the length of this table gets longer, but it doesn't get wider. It always is just 3 columns. And then the number of blanks in each column is equal to the total number of conditions. So we have 2 atomic conditions, so there's 2 blanks. So if you look at row A there at the very top example of the table, so we've got row A, and there's true, and then under true, blank, blank, false, and under false, blank, blank. And those 2 blanks are used to hold the value that you want the atomic condition to take on. So now we've got the blank table. So the table at the very top, the first of the 4 example tables there at the very top, that's what you have at the end of step 2. Now in step 3, what we do is we just fill in the diagonals, diagonal blanks. And the second column, it's with T or for true, and in the third column with F. So in other words, if you look at row A in the second example table there, what that's saying is I want the value, the atomic condition A, to take on the value true. That's the first entry there. And I also want it to take on the value false. That's the second entry. So A is true, first entry. A is false, second entry. Now the value that we want B to take on is still blank. That's why we still have the blank, the underline there, right? Now, if you look at the B row, what we're saying there is that in the first test corresponding to the T column, we want B, the atomic condition B, to take on the value of true. And in the second column there, we want the atomic condition for B to take on the value of false. Now, that brings us to step 4. So what we do is we replace the remaining blanks with neutral values. Neutral values meaning values that will not affect the outcome. So I just discussed that a moment ago, right? So if we're dealing with an OR operator, the neutral value is going to be false, because what that does is that allows the other condition to drive the decision being taken. Remember, we want each atomic condition to force the decision to be taken at least once true and once false. So what we have there is in the first row, if you look at the third example table, so it says A, T, in the A row we have A is true and B is false. So what's the outcome going to be? What's the decision? It's going to be true, right? So true or false is true. And then in the second column there, the false column, we have false or false, right? And that's going to be false. Now notice that in both of those cases, the condition A was the condition that drove the decision being taken because we used neutral values for B. Now in the B row, we do the same thing except allowing B to drive the decision. So we replace the blank that preceded B with a false, and we replace the blank that preceded B with a false in the F column as well. So false or true is going to be true. False or false is going to be false. Okay. So we've now populated the table, and then what we do is go to step 5, and we look for duplicate tests. So we have true, false, false, false in the A row. And then in the B row, we have false, true, and again, false, false, which is redundant. We don't need to run that fourth test, so we can delete it. So as predicted, we had n atomic conditions, n equals 2 in this case. 2 plus 1 is 3. We have 3 tests. Now, let me just show you a more complicated example here. I don't want to dwell on this too much because I don't want to spend an inordinate amount of time talking about MC/DC coverage, but I do want to point out that you can have more complicated example like the one here. So in this case, we have 3 atomic conditions, A, B, C, and the logical expression is parentheses A or B, close parentheses, and C, okay? So we still have 3 columns, the logical expression, true and false. But what we have now is we have 3 rows on the table. We have an A row, a B row, and a C row. And in the true columns and the false columns, we have 3 blanks rather than 2 in the previous one, right? So far, pretty similar. It's scaled downward, as I said, and each of the columns has gotten slightly wider, but the total number of columns is the same. And the population of the diagonals with the trues and falses you see in the second example table there, that corresponds to step 3. So far, so good. Now, when we get to step 4, we replace the remaining blanks with neutral values. And again, it's false for or and true for and. The thing is that you have to be a little bit careful with compound expressions like this, because notice that when we're dealing with the A or B expression, then we're going to be using false. But when we're dealing with the overall quantity A or B and C, then the value of that sub-expression A or B, the neutral value there is true. Now, we can do any combination of A or B that results in that neutral value of true. So that's why if you look down at the C row in the third example table, I have true, false in the true column and true, false also in the false column. Now, you might say, well, wait a minute, what are you doing using false there? Because the neutral value with an and is true. Well, yes, but all I care is that the sub-expression A or B comes out to be true. The individual atomic conditions within the A or B sub-expression can be any values I want as long as they're not both false, because true, 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 false, and false, true will all have an outcome of true for A or B. Now, the reason that that's important, that ability to kind of play around with those values, is because if you don't do that right, what will end up happening is that you will not get n+1 tests. You might get n+2 or more tests. So sometimes there's a little bit of playing around that is necessary in these compound expressions to generate tests that are identical and can be deleted. Now, again, I don't want to spend a whole lot of time belaboring this point if it's not clear what I said, or if you'd just like to work this out on your own. What I would invite you to do is pause the presentation at this point and actually work through this example as an exercise and make sure you can get the same answer I did. And if you don't, then back up and listen to my explanation of this example again. Okay, so statement coverage, decision coverage, MC/DC coverage are all in relatively common usage. MC/DC not quite as common as statement and decision. I mean, pretty much any code coverage tool that you would tend to have in your build pipeline would probably have the ability to give you statement and decision coverage, might or might not have the ability to get MC/DC coverage. If you do need to get MC/DC coverage because you're working on safety critical systems or they're just high risk mission critical systems, you may want to actually make sure that your tool has that capability. Now, there's another thing that you're likely to find in static code analysis tools, like, for example, SonarQube, I believe, has the ability to do this, and CheckStyle for Java tool CheckStyle has the ability to do this. And this is measuring what's called McCabe's cyclomatic complexity. Now, cyclomatic complexity goes way back to the mid-1970s, and if you read McCabe's paper on this, which you can get from the National Institutes of Standards and Technology website, that's nist.gov, and do a search for a paper that has the phrase structured testing in the title. You can download McCabe's paper, or at least an updated version of it. She co-wrote with a guy named Thomas Watson. And no, I don't know if that's any relation to the Thomas Watson. Anyway, in that paper, McCabe describes use of graph theory to create a directed graph that illustrates the control flow, and then of a procedure or method, and then calculates what he called the cyclomatic complexity based on that. And it looks very similar to a flow chart that you might have seen before, except that you have circles, which he referred to as nodes, that represent the entries, exits, and decisions, and then edges, which are shown as arrows, are the non-branching, non-looping statements. Now, before I get into the theory of this and explaining how to use it, let's talk about practically why this might matter. So what McCabe was getting at was, why are some methods or functions inherently more buggy and harder to maintain and easier to break? And he said, well, it has to do with complexity. The more complex something gets, the easier it is to introduce bugs into it, and this includes during maintenance. So when you go to maintain it, it's really easy to break it. And what he said was that the complexity should be limited to 10. And I'm going to explain how the complexity is calculated here in a minute, and get to how a quick rule of thumb for knowing what complexity is. But that is where he set the limit, was at 10. Now, you do have to be a little bit careful with this, because it is possible to have certain methods or functions that can have a cyclomatic complexity that's higher than 10 and still be perfectly maintainable, particularly those that use switch case constructs and may have relatively long switch case constructs, and which gives a traditional cyclomatic complexity that's very high. But there is something that's called a modified cyclomatic complexity, which does not increase the complexity for switch case constructs. It's not, the case blocks are not seen as increasing the complexity. So you do have to be a little careful with that threshold of 10. Boris Beiser, in his book, Software Testing Techniques, if you have access to that, has a very good write-up of various kinds of complexity metrics and a discussion of how to use them with care, which I would encourage you to do if you are working on a project where cyclomatic complexity is in use. Now, one of the other things that's true with cyclomatic complexity is that it turns out that the number of basis paths is equal to the cyclomatic complexity, and the number of basis paths is also equal to the number of basis tests necessary to cover this graph that is created. And the number of basis tests that will be generated turns out to be exactly the same set of tests necessary to achieve branch coverage, which I was talking about before. So if you insist on not just decision coverage, but also branch coverage, you will get that test that I was referring to earlier, that test that involves doing the body of the loop, but also not doing the body of the loop. And I'm going to show you how that's an outcome here in just a second. Okay, so we go back to that Fibonacci code that I showed earlier, and let's draw the cyclomatic complexity graph for this. Now, I'm going to go through the drawing of the graph fairly quickly, and the reason I'm going to do that is because if you should understand how this metric works in order to understand how it's going to be used. But if you're going to actually use this, you will probably not be drawing these graphs. You will either be using a tool or using a very nifty rule of thumb that I'm going to explain to you in just a moment. So, but anyway, the graph looks like this. You start by drawing an entry and an exit node. So that's the top and the bottom nodes. And then for every sequence of 0 or more non-branching, non-looping statements, you draw an arrow called an edge. And then when you get to a branching or looping statement, for example, the if n less than 0 statement, we then draw another node, and we have a yes branch and a no branch, a true branch and a false branch. Okay, and that same thing continues down. So we have the true branch there, the yes going to exit, and then no goes to the else. And then we get into the non-branching, non-looping statements inside the else block. And then we get to looping statement 4. So there's another node. And you see there's the no, which goes down to the exit. But there's also the yes, which goes back to that same node. That represents the loop, naturally enough. And it looks like a loop, right? So we're going to calculate cyclomatic complexity, which in the paper is referred to as C. And then there are three other defined terms, R, which is what's called an enclosed region, E, an edge, that's an arrow, and N, which is a node, which is the bubble, as I've explained. Now, an enclosed region just means a region on the graph that is entirely surrounded by edges and nodes. And let's take a look here. The cyclomatic complexity is going to be calculated such that it's equal to the number of regions plus 1, the enclosed regions, and it's also the number of edges minus nodes plus 2. Now, it just happens to work out that way. The more intuitive way of doing this calculation using the graph is to just look at the number of regions. And if you look here, you can see that there is an enclosed region on the left-hand side of the graph. So you look at that edge that corresponds to the yes, the top yes, and then the edge that corresponds to the bottom no, both leading down to exit. And then if you look to the right of those two, they each come out of a node, and those two nodes are connected by the no edge. So that defines an enclosed region. And then there's another enclosed region that's created by the loop, which is the yes towards the bottom there that's coming out of the I less than N node. So there's two enclosed regions. So the cyclomatic complexity is 3. Now you might say, okay, yeah, that's kind of complicated and I'm not sure I could do that. So as I said, what you would really want to do is just use a tool. So in RCube, other common tools can be used to generate this, calculate this, this metric for you. So use a tool. Now you might say, well, what if I'm sitting in a meeting and I'm looking at a chunk of code and I want to estimate what the cyclomatic complexity is? Easy. What you do is you start with 1. So notice that if in the calculation there at the top, number of regions plus 1. So you start with 1, and then every time you see a branching or looping statement, you add 1 to it. So there's the if n less than 0, okay, so that's a branching and looping statement. So now the cyclomatic complexity is up to 2. The else doesn't count because that's part of the if statement. And then there's the for loop, so that counts, okay? So now we're up to 3, and that's it. So 1, if 2, 4, 3. Make sense? Okay, now, so what do I do in terms of connecting this back to testing? We talk about complexity of the code, but how about from a testing point of view? Okay, so we can define what are called the basis tests using this graph. So if I label each one of the nodes with a number, 1, 2, 3, and 4, there are 4 nodes, right? Then the basis paths are defined as equal to the number of basis paths will be equal to the number of cyclomatic complexity. And so what I do, the first basis path, according to McCabe's algorithm, is the shortest path through the code. So that would be 1, 2, and then 4. So that was that first test I give, n less than 7, right? And then the second basis path is a path that covers at least one previously uncovered edge and or node, but it's the minimum number of previously uncovered edges or nodes. So I go 1, 2, 3, and 4. So that would be the test that I alluded to, the one that does not do the body of the loop. Notice that we exercise node 3 only once in basis path 2. And then we apply that algorithm again. There's still one previously uncovered edge, which is the doing the body of the loop. That's that yes loop. So we would go 1, 2, 3, 3, 4. So the McCabe algorithm would say that we should test with n equals some negative values, so -7, n equals 0 to not do the body of the loop, and then n equals 1. Now notice there is kind of a weakness there. N equals 1 is not a particularly interesting test. N equals 20 is a much better test, but McCabe is generating the test purely from a graph theory point of view, not from the point of view of what is this program doing, right? And that's always something you have to be careful of with any of these kinds of tests that are generated purely to achieve a particular coverage metric. The tests are driven by the structure of the code, not the logic of it in the sense of what we're trying to do with it. And that can result in the generation of nonsensical tests. It can also, depending on how the coupling between the different conditions works out and the short circuiting, result in the generation of tests that aren't actually achievable. So you may run into that where it actually, to achieve 100% decision coverage or 100% basis path coverage, it generates some tests that can't actually be run because those particular combinations of conditions can't actually exist in real code. Okay, so we've talked about the control flow based types of tests. So I said I'd mentioned data flow tests. Data flows can be tested a couple different ways. One of the things that you'll find if you do some searching on the internet on this, is what's called set use pairs or defined use pairs, kind of the simplest and most common. Beiser in his book Software Testing Techniques describes a somewhat more complicated version, but set use pairs seems to be the thing that, if you look around on the internet and find some credible papers written on this, it's going to be set use pairs. So basically what a set use pair is saying is that for every variable, we want to identify places where that variable is set and then a subsequent place where that variable is used prior to being assigned a value again. The idea being that if something weird is going on with the data flow, by exercising all the set use pairs, we would be able to see bugs that would exist there. So applying this again to our Fibonacci program here, I've identified the different variables. So I have I, N, PP, P, and C. Those are my 5 integer variables that are declared in line 3, right? And what I do is I go through the code and I look for any place where that variable is assigned a value, and then on what line is that variable then subsequently used. And what you see in the first 5 sets of bullets there are all of the set use pairs identified for the for the different variables. So in this case, if I just run the test that basis path coverage is suggesting for me, which was -1, or any negative number really, 0 and 1, you can see that I would get set use pair coverage for I and for N, but I would not get set use pair coverage for PP, P, and C, because I have to iterate the loop. I said max, but it's really 3. 3 is sort of the magic number to get to the set use pair coverage. And also, if you think about, I want to check for the flow of the value in C flowing into P and then flowing into PP and then back into C, I'd have to iterate the loop at least 3 times. That's why I said the magic number is at least 3. And there are defects, for example, associated with complex data structures or missized data structures that can only be revealed by this kinds of set use pair analysis. Unfortunately, there do not appear to be any tools out there to automate this. There are tools that can help you do the drawing of the analysis, that could draw the picture, but there are not any tools that will allow you to instrument the code and then run tests and that determine the data flow coverage, at least none that I am aware of, nor any that I could find in a recent search on the internet. I'm not sure why that is. I assume it's due to the complexity of the task. Nonetheless, it is a thing which can be systematized, and therefore it could be programmed. I just think that there perhaps has not been enough demand to get people to do it. Okay, so that's an overview of code coverage metrics and white box testing. Let's briefly talk about some limitations here while I get another sip of coffee in. So white box testing is quite a useful thing, and I definitely encourage you to apply these techniques that we've discussed, but it can't find every single kind of bug. It's very useful for unit testing, and I would say, yeah, definitely for unit testing, you want to set the bar at 100% statement coverage, ideally also 100% decision coverage, and for safety critical code, you want to have 100% statement, decision, and MCDC coverage. But even so, you could miss things like bugs of omission. So if you have some code that should be there because there's a requirement that should be defined, but it's not, so there wasn't any code defined for that, well, guess what? You're not going to have code there to test. So you want to use things like requirements, user story, use case, design, code reviews to find those kinds of bugs. Maintainability, cyclomatic complexity helps by defining a standard for maintainability, especially if you use the modified rather than traditional version of that. But you could still have completely bizarre variable names, constructs of different kinds. And I have an example that I've used on occasion that's showing a piece of code that has cyclomatic complexity of 10, but is just very, very difficult to understand. And then another piece of code that has a cyclomatic complexity, traditional cyclomatic complexity of about 150, but is in fact actually quite easy to understand. So to catch this kind of maintainability issues that are not associated with branching and looping, which is really what McCabe's cyclomatic complexity is doing. It's saying that branching and looping are the sources of complexity, but of course there are actually other things that make code complex and thus hard to maintain. You want to use code reviews and static analysis tools for those. And of course, various kinds of systemic problems, non-functional issues related to performance, security, usability, interoperability, and so forth. System level tests, code reviews, black box tests of various kinds are what you're going to need to find those. So just because you very, very thoroughly tested the code and your code coverage metrics show it, doesn't mean that you have found all the bugs. Okay, so just to briefly recap here, white box testing again is a form of dynamic testing that involves running the item under test and it's based on how the code works. We looked at three main theoretical techniques, the first two of which are also in use in practice. So that's the code-based control flow techniques of statement and branch coverage, and the modified condition decision coverage, or MCDC. Tools exist to look at those during your automated tests. Cyclomatic complexity and basis paths are also tools that exist for that. So that's both, there's theory behind it, but also actual practical tools available. And we looked briefly at set use pair or data flow coverage, and regrettably, there are no tools available for that. But in the case of the first two of those techniques, tools are available, and I would encourage you to use those tools, because while I've explained how to do this manually, I think you can see that any attempt to do this manually in practice would be tedious to say the least. And again, just to stress, white box testing by itself is an incomplete solution. It's complementary to black box testing, and also complementary to static tests like static code analysis and reviews. So you really want to use all three to form a complete testing strategy, and not over-rely on any one of these, whether it's over-reliance on black box testing or over-reliance on white box testing, which are problems that I see sometimes with clients. So I would encourage you to avoid those. All right, and that concludes the talk here. I'll put up some information on how you can connect with me and with my company, RBCS. You have LinkedIn and Twitter coordinates down there. So if you'd like to follow me or connect with me, I'd be happy to have you do that. If you want to include in your LinkedIn connection request that you came across my information on Luxoft Tech Talks, that would be great. Help me understand how you came to connect with me. So thank you all for your time and attention. I hope this has been a useful presentation for you and increases your technical testing skills with respect to white box testing and code coverage.